So, all right. So today we're going to be maybe taking a little step back, but important establishing some vocabulary so we can talk about certain things in the same language. And again, you know, some of this you may know, some of this you may not know, some of this, you know, I want to just make sure that you have good background knowledge on. So, you know, just be patient as we kind of work through this. But I also want to lay a little groundwork for some things that are coming down the line next semester, like when we get into trigonometry, okay? Because trigonometry really means the study of triangle measures is what we're talking about. And so I know that triangles in 2024 right now in your world with TikTok and all the things that you guys do with all your athletics and everything, like it may not seem like a big deal. But back in the day of these people that you know, we did these projects on, and, you know, these people were studying math in the 15, 16, 1700s, like that was the hot thing. If you were doing math, you were doing math about triangles, because there's a lot of relationships in triangles, and there's so many foundational principles for all of geometry in the basic parts of triangles as well. And so we just want to make sure that we have some good, solid background on our foundation going into this, right? So one of the things we're going to talk about today is classifying triangles. And we can do this in two different ways. We can classify them by their angles, and we can classify them by their sides. And actually, we're going to do both, and that's how we're going to name our triangles. All right, so let's just kind of start with some triangle examples you have up here. So you can see that we have a triangle that's got three acute angles. Quick, tell your neighbor what it means to have an acute angle. Good. You should have told your neighbor that it's an angle that's less than 90 degrees, right? So if we have a triangle that has three of those, then we just call that simply an acute triangle. All right. Now, if you have a triangle that has one obtuse angle, and you can actually only have one obtuse angle, we'll talk about that later. But if you have that, then this is called an obtuse triangle. Tell your neighbor real quick, what's it mean to have an obtuse angle? Greater than 90 degrees, and what? There's two parts to it. It's greater than 90 degrees and less than 180 degrees. Exactly. Good. Okay, and so then we would call this an obtuse triangle. And of course, if we have a 90-degree angle in there, right, we have our right angle, then this is just called a right triangle. And again, right triangles are going to become big for us next semester because we're going to be doing right triangle trigonometry, right? And that's kind of the introduction to trigonometry. When you get into functions in trig class, after Algebra 2, you'll do all different kinds of trigonometry. But for us, we're just going to focus on the introduction to that, which is right triangle trigonometry. Now, those three, I would imagine everybody in here should be pretty familiar with. Let's talk about this last one here, though, right? So you can see here I've got these congruence marks through the angles here. Anybody know what this one is called, Pedro?
Is it an equilateral?
It is not an equilateral triangle yet, but here's the thing, right? Lateral refers to length or side length. So when we say equilateral, we're talking about three equal side lengths. But that's not what's equal here. What's equal here? That's a good try. It's a good guess. Anyone who want to take a shot? Go. I can't hear you. Yeah, that's exactly right. It's actually equiangular. That's what we call this type of triangle here. So we're going to write that equiangular triangle. So when we know that we have these three angles that are equal to each other, then we call this an equiangular triangle. Okay, now let's jot some notes right down over here underneath this word angles. And let's say this. So in triangles, an angle's size is directly related to the length of its opposite side. And we're going to do some underlining here. So we're going to say an angle's size is directly related to the length of its opposite side. Okay, everybody look up here for a second. All right, watch me. So I'm going to make an angle with the palm of my hands. Right now, I want you to imagine a line stretching between the tips of my middle fingers here. Right? Picture that. Right? Now, when I take that angle and I make it bigger, what happened to the line that stretches between my fingers? It got longer, right? When I take that angle and I make it smaller, what happened to that line? It got smaller. So the size of an angle has a direct impact, a direct relationship with the length of its opposite side. Now we have this opposite language already going for us because we just talked about vertices and their opposite sides and altitudes connect them at 90 degrees, right? Or midpoints go back to opposite vertexes. So this idea of going across the triangle, right? And so let's just jot a little note over here, right? Let's take this obtuse triangle here and let's just I'm going to highlight this a little bit. You can just sort of indicate it however you want in your paper. But this angle right here is clearly the biggest angle in our triangle. This is an obtuse angle, right? And that is clearly across from the longest side, right? So the longest side is going to be opposite that biggest angle. Now, if we talk about this other triangle, this right triangle right here, right? We have our 90-degree angle. What kind of an angle is this one right here?
Right.
No, that's not a right angle. What is that? And how about this one? That's also acute. Okay, so we have an acute angle up here, and we have an acute angle down here, right? And of course, we have our 90-degree angle. So if the acute angles are less than 90, then the 90 must be the biggest angle. And so projecting across the triangle to the opposite side, we have the longest side of a right triangle. What's that called? That's the hypotenuse, right? So that's why the hypotenuse is always the longest side in a right triangle, because it is opposite the biggest angle inside that triangle. Okay, now let's think about this one. If I've got an angle of measure, and it's projecting across to its opposite side out here, and then I have an angle of the same measure projecting to its opposite side over here. Think about it for a second here. Watch up here again, right? So let's say I take this angle that's over here, and I've got that line stretching between my fingers, and then I rotate the angle this way. What happened to the size of the line? It didn't change at all, right? So the same angle projecting the same side length would create equal side lengths all the way around, like that. See how that works? And so, Pedro, when you said, is it an equilateral triangle? And I said, well, not yet, because now we can see that it is, because all equiangular triangles, by that connection of the angle's relationship to its opposite side, must be equilateral. And so all equiangular triangles are also equilateral. All right? Does that work the other direction? Can I turn around and walk the other direction on the same sidewalk? Are all equilateral triangles equiangular? What do you think?
Yes.
Yeah? No? Yes, no? All yes. Yeah, of course, because if you start with an equilateral triangle, the only way you could have gotten there was from an equiangular triangle, right? So those two have to go that way. Now, I gave you a special term for that. There was the geometry term for turning around and walking a different direction on the same sidewalk. Do you remember what that term is? Begins with a B. Begins with a bi. No, it's not bipolar. No. Bi C. CO. No, sectional would be S. By what? No. Good try. Biconditional. The condition works in both directions. So that's the geometry term for when we can turn around and walk a different direction on the same sidewalk. Okay, good. All right, so here's what I want you to do. I want you to do 1 through 5, just 1 through 5, and I want you to categorize the triangles you see in the picture there. And just real quick, just make sure we're clear on this, right? These letters in here are the vertices of the triangles, right? So triangle CDE starts at C, stretches to D, comes back to E, and then goes back to C like that. So it's C to D, D to E, E to C. All right, go ahead. Categorize those by their angle groupings. What angle groupings do they go with? All right, let's take a look. Did you come up with these right here? Yeah. Let's see who got all of them right. All the way around the room. Let's see. Who got it right? Yeah. Good. Okay. So then let's talk about classifying our triangles by their sides. All right. Well, now we already talked about this one a second ago, right? When we have these three congruent sides, then this one is called our, now we're classifying by its sides. So this time we're going to call it equilateral. Okay. So it's different organizations, right? Okay. All right. Now with this one, what I want you to do, see if you can follow my instructions. I want you to put some congruency arcs in the angles, and I want you to match the number of arcs with the number of hash marks that the angle projects to the side. Let me say it again. I want you to put some congruency arcs inside the triangle on the angles, and I want you to match the number of arcs with the hash marks that you see on the side that angle projects toward. Okay, the angle projects toward a side, right? Okay, match the congruency arcs. Let's see what you can do with it. Give it a shot. Followed what I wanted, you should have done that. Yeah, right? Number of congruency arcs match the hash marks on the side it projects to, right? So this angle down here is projecting to this side over here, one congruency mark for the hash, so then one arc here. Because they're all one congruency mark, we have one mark through here, and so then we can again see that equiangular, equilateral connection. Okay? All right, then, let's talk about this one. I don't particularly care for the way this drawing is marked. I want to update this. We're going to go like this right here. So let's put 2 hash marks there. Okay, so now we have a triangle that has 2 congruent sides and 1 not congruent side. Everybody remember what this one's called? This is your isosceles triangle. All right, isosceles triangle. All right, good. Okay, again, I want you to put some congruence arcs in the angles, and I want you to match the number of congruence arcs to the hash marks on the side the angle projects toward. Okay, go ahead and do that. You're going to put that. How'd you do? Yeah? Okay, now, there's some particular vocabulary that goes with this that you need to know. So let's take a note of some of this vocabulary. So these 2 congruent angles down here are called the base angles of the isosceles triangle. These are your base angles like that. And this top angle, the non-congruent angle, this one is called your vertex angle. Okay? Now, when we see this like base angles, right, we think, okay, well, base, they're on the bottom. I see my picture drawn like this. It's the angles that are on the bottom, right? However, keep in mind, I could do something like, say, I don't know, let's just do this. Okay, so I could do this, and now my base angles are no longer on the bottom of my triangle. Really, and probably, this is probably more close to the bottom of the triangle. Right? So what is important to understand is that the base angles are actually the 2 congruent angles in the isosceles triangle. Remember, however we rotate that triangle and position it, when we have an isosceles triangle, we're going to have 2 congruent sides. You should be able to use those sides to find the congruent angles, again, or vice versa. You should be able to use the angles to find the congruent sides and be able to label base angles and vertex angle no matter how we rotate that around. Does that make sense? Is everybody good there? Okay. All right, let me put this back to where it's supposed to be. Makes it a little hard to write, the other direction like that. Okay. All right, good. Last one. Let's do this, this, and this. Everybody remember what this one's called? Scalene. This is your scalene triangle. Good, right? Okay, so this language that you're familiar with, right? This is side classification language, right? So just keep that in mind. This is your scalene. All right, matching number of congruent arcs inside your angles to projected sides. Go. Scalene. What is what? S-C-A-L-E-N-E. Yeah. All right, so you're putting in your, should have looked like that. Good? Okay, now listen, little disclaimer. This is not a hard and fast geometry rule that you will always have matching arcs with the opposite sides, okay? But what I'm doing here is I'm establishing for you the connection between the length of its opposite side and an angle, which is going to be a very important connection for us as we move down the line, especially when we get into our trigonometry, okay? All right, so you are going to take these triangles that you see in this picture over here, and you're going to classify them by their side names. Again, if you don't have a congruency mark, then what you can't assume anything about that side. Just you can't assume a 90-degree angle. So you can only use the congruency marks that you have. All right, go ahead and do 6, 7, and 8. All right, should have come up with scalene first, isosceles second, equilateral third. Everybody solid? Yep. Okay. Now, let's put the whole thing together. When we name triangles, right, like when I run an attendance list or a roster for my class, I have it set up so that it goes last name, comma, first name. And that's how I sort you guys so that I can keep track of everything, right? Well, the same thing goes with naming triangles. There's a particular way that we do that. We name it angles, comma, sides. That's the naming technique that we use for naming triangles. So like, let's take this first triangle right here, number 9. According to its angles, what classification does that fit? Right. Okay. According to its sides, what classification does that fit? So then this would be a right isosceles triangle. Yeah. Just like I would capitalize Kazera's Quinn. Okay? All right, let's talk about number 10. So number 10, based on the information you see from an angle perspective, what would you say? Okay, from a side perspective, what would you say? That have to be scalene because we don't have any markings, right? So then this would be an obtuse scalene triangle. Why don't you write down number 7? Let's see how you do. Give it a shot. Okay, this one you should have put equiangular equilateral, right? Okay, now let's talk about something. Could I call this one, number 11, an acute equilateral triangle? I mean, it fits the definition, right? Because why? Biconditional? I mean, the names are biconditional, yeah. But by definition, an acute triangle has 3 acute angles. Does that have 3 acute angles? Yes. So then by definition, it fits that, right? Yes. Just like by definition, if you go to school here in Fresno, you are a student. But if you go to school at San Joaquin Memorial, you're a Panther, huh? Right? That's a more specific name, like we talked about before, right? Just like complementary angles is angle addition postulate to 90 degrees. It's a more specific type of angle addition postulate. And we always want to use that more specific name, and that's why we wouldn't say acute equilateral, we would call it equiangular. Make sense? All right. So I'm going to give you about 4 minutes, and I want you to do 12 through 20. You have 4 minutes, 12 through 20, naming triangles. Last name, comma, first. Last name, comma, first. Or angles, comma, sides. Ready to go. What you should have come up with here. Yes. Okay. Let's talk about 12, 13, 14 first real quick so I can zoom in. Everybody good on 12, 13, and 14? Those should have been fairly easy, right? Okay. So really the challenge becomes picking these out of this larger picture here, right? That's where the challenge kind of becomes. And so just some things that you should know too that you can see, right? You've got vertical angles here, so you should know that that's a 90-degree angle. You've got your angle SRT being bisected. You know U is the midpoint of RT. So that gives you some more information. So TQU, so that's this triangle right here, TQU. All right, so we kind of have to build this information, right? So for example, we know that from R to U is 8 millimeters and a single congruence mark here. Now we have a single congruence mark here, which makes that 8 millimeters because they have to match. But we also know that this is 8 millimeters as well, because use the midpoint of RT. And then because this is 8 millimeters, it gets a single congruence mark. And because this is an equilateral triangle, it must also be an equal angular triangle. Make sense? All right. Any other questions on those? How do we know for sure that QR, how do we know that this is not an isosceles triangle? How do we know, like, because like, let's take SR, for example, that's 16 meters. How do we know for sure QR isn't 16 meters? Pierce?
Well, if there's like a right angle, then it's like impossible for like any other side to be longer than that.
Okay, all right, good. I like that. I like that. So this would have to be the longest side because it's the hypotenuse of a right triangle. Good. That's a good argument for that. Okay, somebody give me a different one. What would be another way, Pedro?
If you find the height, if you like, since you already know the hypotenuse, you can do like the thing, you can do the equation and find it.
The equation? What equation? What are you talking about?
And so where it's like the hypotenuse equation, but then you have to like subtract from each side. Oh, it's like a squared. Never mind. It's b squared equals c squared, and then you subtract a squared from each side.
What's it called? Somebody want to tell them what's it called? Pythagorean theorem. Very good. All right. Yeah, you could use that, Pedro. That's for sure. Yeah. Pierce, you got something else?
Yeah. Well, because 90 degrees is the largest angle, so the opposite side has to be like the longest side.
Well, that's kind of what you said the first time, the hypotenuse. It's the same thing. How about something totally different? How about something we talked about today? Could anybody apply something we talked about today to this? Well, my question is how do we know it's not isosceles?
Because there are no congruence marks.
True, but we didn't really talk about that today. But yeah, but true. I mean, we could use that. But what was something specifically we talked about today? What about the line? Right?
Since the angle as 60 degrees, it's going to be the line Q is going to be shorter than SR and longer than SQ.
Right, because the angle that's projecting is different for each side, right? So a 90-degree angle is going to project a 16-meter side. A 16-degree angle is going to project a degree side, or a measured side, and a 30-degree angle is going to project an 8-millimeter side. And so because of the different angle measurements, then we know for sure that the side lengths also have to be different as well. All right, good. Okay, so let's talk about classifying triangles in the coordinate plane. Here's what I want to do. Let's draw ourselves a little XY coordinate plane over here like that. So just draw yourself a little scratch XY coordinate plane over there. And let's find this triangle JKL from number 21. Let's kind of ballpark these. So I want you to put a point like about where you think -7, -7. We're going to do all the little hash marks. We're not going to count it out exactly. Like just ballpark it. Where do you think point J would be at -7, -7?
Down. Maybe the lowest one.
What quadrant would it be in? Anybody want to give me a quadrant number? Yeah, third quadrant, right? So it's going to be down here, right? Like maybe here-ish, something like that, right? Okay, so if that's where J is, where do you think K might go? Okay, good. Second quadrant, right? Pretty close to the axis, right? Which axis? The X or the Y? The X-axis, right? Because it's going to be out here at -9, right? So like K will be out there. And then L, what quadrant is L in? Third one, right? -1, -1, right? So we could put L like here-ish, right? And then if we connect those points, like that, and then that, and then that.
Oh, I get it.
Now we want to try to classify this according to its side. So in order for us to do that, we would need to know the side lengths of each of these three sides. Do we have a tool for that?
Oh, it's the one we have.
Oh yeah, our distance formula tells us the distance, right? It's basically like doing the Pythagorean theorem, right? So like if we wanted to know how long JK was, right, we could say JK is No, we're never done with this.
I thought you left formula.
Never done with the distance formula. All right. So you could do this. We could do JK, and then you could like give me one level of work out here, and then you could give me like an answer out here. And I'll tell you what, just leave it in just regular old radical form. You don't even have to simplify it. Just plenty old radical form is fine. We'll just leave it out here, and let's see what you come up with. But of course, to classify, you're going to need JK, you're going to need KL, and you're going to need JL, like that. All right, ready?
What's the formula again?
Go.
What's the formula again?
I'm not going to tell you what the formula is.
X2 minus X1 plus Y2 minus 1.
All right. Good for you. Good for you. All right. So what kind of a triangle is this if we classify it by its sides? This is an isosceles triangle. Very good. All right. So now we know how to do that. Should we do another one? Okay. All right. Okay. Sounds good. All right. Then let's do something else. All right. Here we go. There you 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 Okay, all right, here we go. Okay, first one, number one. All right, look up here. We have what kind of a triangle do we have in number one?
Equilateral.
An equilateral triangle. Okay, so let's put some congruence marks where we know we can put congruence marks for the sides. Yeah, right, we put one on each. Good, so we go boom, boom, boom. Now, here's what we're going to do. Watch carefully. This, I don't particularly care for this M up here because that's supposed to be 49 meters, but that could very easily be confused with a third variable, especially since we have an X and a Y. So we're just going to cross that out because we don't really use that as we're doing these types of problems anyway. So you have an equilateral triangle. One side is 3x plus y. The other one is 18y minus 41. The other side is 49. Solve for x and y. Ready? Go.
They're all different units. That's impossible.
You should have done was something that looks like this. All right, so once you've solved that, which should go pretty quick, you should have come up with x equals 16 and y equals 5. All right, good. Yes, sir. No, we're leaving them off for this one. All right. Triangle RST is an equilateral triangle. That means we can put a mark on each side, right? All right, and we want to solve for x and then find the measure of each side. So here, look up here. This is what I want you to do. Right here, I want you to show me your solve for x work, okay? And then over here, I'll show you what I want to see for your find the measure of each side. All right, so let's start with your solve for x work. Ready, go. Okay, if you're moving in the right direction, you should have started here.
I got 8.
Or could you have started somewhere else?
Yeah.
Yeah, actually, there's 3 different places you could start, huh? Because they're all equilateral. Wherever you started, you should have ended up here. Yeah? All right. Here's what I want you to do. Over here, I want you to jot down your 3 side lengths like this. And then you're going to show me the work for those 3 side lanes using the fact that x is equal to 8. Let's see what you come up with. Go ahead. All right, you should have come up with that right there. Yes? Okay, now listen. Perhaps you may be thinking to yourself, hey, Mr. Vargas, I know this is an equilateral triangle, so if I find one of them, don't I know the other ones are all 74? True, unless you did it wrong. Then you're going to get all three of them wrong. So what I do want you to do is I want you to actually show me the work for all of the sides of the triangle. Okay? All right, let's jump down to number 4. All right. Place some congruency marks where you think congruency marks need to go on the triangle on number 4.
Where we think congruency marks need to go?
Where congruency marks need to go on the sides for the triangle number 4. Put your congruency marks, you should have done that right there. All right. So then, given that information, you should be able to set up an algebra problem, figure out x, and find the length of the 3 sides. Ready, go. Okay, here's what you should have come up with for number 4. Good? Okay. Let's go to the back side. Let's take a look at number 7.
We were supposed to
7. All right, so listen, there's no picture for number 7,
Bro, I can't believe the other
but we could draw one. So here's what I want you to do. This is how I want you to start this problem. I want you to draw an equilateral triangle. I want you to put the appropriate congruent marks on that, and then I want you to write next to each side of the triangle the algebra that's given to you in the problems. So create a visual for this question. All right, go ahead and do that. Create a visual for this question. You're drawing an equilateral triangle with congruence marks and writing in the algebra, and you're going to get it. You're going to obviously have to label your corners a certain lettering. All right, let's see what you could do in coming up with the picture for this question. Go ahead. 7. We're doing number 7. What you should have come up with here. Now, your letters might be in different positions, and that's fine as long as the stretch of segment ST has a 2x minus 1 on it, the stretch of TU has an x plus 11 on it, and the stretch of SU has a 5x minus 37 on it. You're good to go. Did you guys get your picture set up correctly? Because from there, it should be pretty easy to do. So we're not going to take the time to do this one. And the isosceles works a lot like this. You just draw yourself an isosceles triangle, put in your congruence marks, label your triangles, get everything on the right place. Once you have your picture drawn, the math should flow pretty easily. All right, let's talk homework. This is an aller. Here you go. Now, the problems that you have left, these would be good ones to save for practice problems for getting ready for your assessment, right? So the ones that we didn't do in class, you are not required to do for homework, okay? But the ones on this page, you are required to do for homework.
Oh, are you serious? I just
All right, I tell you what, I'll give you a little bit of a break. You can cross off number 11.
Yeah.
Okay? But you got to do number 10. I don't really know. I haven't looked at it, so I just picked one of the distance ones.
Oh my gosh.
Yeah, and if you don't do number 10, then I'm going to make you do number 11 right there on the spot. So. Okay. Good job today. Woohoo! Geometry rules.